All right, so for our project, we did YouTube comment sentiment analysis, and I'm Nick.
I'm Nate.
So for an introduction to our project, we wanted to be able to classify YouTube comments as positive, negative, or neutral, and there's a couple of reasons why you might want to do this. So one would be benefiting users for getting rid of harmful content, and then another reason could be getting insights into viewers' reactions to some content creators' videos, and they can kind of see how the public is reacting to their new videos. And then one challenge we ran into was for pre-processing the text, we had to get rid of emojis, slang, and special characters.
So as for our data set, we got it off of Kaggle. This data set contained around 18,000 unique comments, and it's a heavily imbalanced data set. So negative comments or negative sentiment comments account for less than 15%, and positive comments are over 60%, which can lead to models biasing towards positive, obviously. And to combat this, we use SMOTE as a resampling technique. And this on the bottom is just word clouds that we generated to show the frequency of some words that were, for example, associated with positive comments. So some main ones are like love, thank, great, and good.
And for some research we did before this project, we found that earlier studies use machine learning models like naive Bayes algorithms or support vector machines or ensemble models like random forest. And when looking into more recent studies, we found that people were using models like LSTMs, CNNs, and transformers, and we plan on looking into model architectures like these for our next phase.
So as for our methodology, going off of our literature review, we wanted to have a few baseline models. So what we used were just the traditional methods like naive Bayes, support vector machines, and random forest trees. And then the two advanced methods that we intended to explore here are the word-to-vec associated with an SVM model, and we wanted to use an SVM model with co-occurrence singular value decomposition. And what we used just for performance evaluators were just the four usual, so accuracy, precision, recall, and F1 score. And the main one we followed was F1 score, which basically takes into account the precision and recall.
So for our experiments, you can see some of the results here. The top three best performing models all used IDF. And then you can also see, we noticed the precision was pretty low for this artifact, and that's why we ended up looking into it and found this.
Yeah, so looking into our confusion matrix that we printed off for the support vector machine model with word2vec, we noticed that it had 0 predictions towards negative sentiment comments, and we believe that this could just be attributed to the class imbalance issue in our data set. So after averaging the vectors, obviously the majority class, which is positive, can dominate the representation, which would cause the model to bias towards positive predictions.
And then here's just another look to visualize how our models stack against each other. And this is when we first saw that this precision was notably low, which is, again, how we looked into that.
Some other plots that we had were the TS and E plots, and this one we did on the left was predicted labels, and then on the right is true labels. So this is of our best model, so the SVM model with hyperparameters that were tuned and TF-IDF. And as you can see, the two plots are very similar to each other, especially in the groups.
And then here's one example of words that were similar to video that we got from our TS&E graph. So you can see words like videos, channel, content. These are all very similar words. And then you also have things like amazing things, amazing episode.
And taking a look at some of our misclassifications. So in this table, we just printed off a couple specific examples of misclassifications. One thing we noticed were there were a lot of ones that were foreign languages that were just counted as positive. So the third one from the bottom is a Vietnamese comment that was misclassified. And this one is tough because our model is trained mainly on English-centered comments. So it's going to have a tough time discerning what the sentiment of that comment would be. Another example is on the bottom, you have your friend's ZHC, interesting. So some things like gibberish or just abbreviations that we couldn't really account for specifically might make the model unsure of what to predict too.
And so in conclusion, our best performing model was an SVM model, which we did hyperparameter tuning for. And to do this tuning, we did grid search to find the optimal parameters. And we're planning on the future on using something like BERT, which is a retraining model. And then we're also using deep learning techniques.
So next here, we'll just go over our code, go through.
So this is our code. We start out with importing our libraries, and then here is our Kaggle data set. So we just display the first 5 rows to ensure like we were loading it correctly, and then down here you can see the class distribution. Here's the percentages, but you can just visualize to see that positive is greatly outweighing the others.
So here's our function we made just to pre-process our text. So some of the things we did, like removing URLs, user mentions, emojis, punctuation, and then we tokenized it. And here we removed stop words, but we took out some specific cases. We left them in actually, such as like not, don't, wasn't, didn't. So these are pretty important to some comments we noticed, so we left them in. And then we just applied pre-processing here, compared some examples from the original and the process text. And then after this, we visualized the word clouds for each sentiment. So here are the original and processed examples, and then here are the word clouds for positive, negative, and neutral that we already went over in the PowerPoint.
Here we do our 80-20 train test split, and then our actual vectorization for parameter for max features. We chose 5,000, and here we have a function to evaluate our models. So the models we have here are the multinomial naive Bayes, our SVM, our random forest, and then we compared all these models and their scores. So we just go down here. You can see a visualization of how these models stack up against each other. So this cell is where we did word to vec, and you can see here we do our tokenization, and then we create our word to vec model. This function is for making the document vectors for word to vec, and then here we actually train our classifier, go on to evaluate our model, and then down here we do one example of word similarity with the word video. We already talked about this in the presentation.
So here, we noticed of our baseline models, the SVM TF-IDF model worked the best. So we wanted to incorporate some like hyperparameter tuning using grid search to see, if we could improve this model that much. So here we just use grid search with these parameters, and then we found that the best ones were a C of 0.1 and a balanced class weight. And looking back, I believe this F1 score was improved by about like 0.05. And then here's just our confusion matrix for it.
So in this cell, we just have a sentiment prediction to just test on these sample comments. So this one is obviously positive, this one is negative, and this one is neutral. And with our best model, we got these correct.
So here, we looked at one of the advanced models that we wanted to explore, which was the SVM with co-occurrence singular value decomposition. So here, we just trained an SVM classifier on the LSA features that were created with a truncated SVD. We evaluated it, and then we printed off a TS&E visualization for it. So Here we just have the evaluation, and then here's our TS&E plot. So as you can see, this large group was just attributed as positive. So this is just part of our data set imbalance issue.
And then here we have just a summary of all of our models against each other, and we also presented some of our conclusions, but we talked about this in the presentation as well, comparing the performance of the models against each other. And again, like we said right here, we saw low precision, which is
So after we compared all of our models and then saw, the hyperparameter tuned SVM model worked the best, we wanted to see if it would perform better on a data set that was sampled with SMOTE. So here we just resampled with SMOTE, and then we noticed that the F1 score and accuracy were noticeably lower. So I believe before it was 0.75, and that was the results for this experiment. And in here, we just printed off TS&E visualizations for each classifier. And this was just between the predicted and true labels. So this is the true labels for naive Bayes, and then this is our predicted labels. This is true for just the baseline SVM, and then this is predicted for SVM, random forest right here. And then this is our best SVM, so our hyperparameter tuned one, and as you can see, it looks very similar. We went over this in the presentation too, and then we went over, this is our co-occurrence SVD, and then our word-to-vec SVM.